Hi guys, welcome to this revision session on specific latent heat. So this session, what we're going to do is going to define what specific latent heat is, calculate it, and then combine it with specific heat capacity. So specific latent heat is from P3 exclusively, matter and particles. They do combine it a lot with things like specific heat capacity, but also internal energy as well. So there are other videos on those if I do mention them and you're not sure. So let's look at this to start with. Imagine I have a substance and I start heating the substance, so I transfer heat energy to it. What happens to that substance over time? Well, if we measure the temperature as time goes on, we can see that to start off with, the temperature is increasing from 20 to 50. Then the temperature stays constant at 50. Then it goes up from 50 to 80. Then it stays constant. And then it goes up again from 80 to, on this graph, just past 100. So what's going on here? Well, if we look at the first stage, what we're actually doing is when we're supplying the substance with heat energy, that heat energy is used to make the particles go faster, and we're using it to increase the kinetic energy of the particles. So whenever you have a substance that's increasing in temperature, what you're doing is you're increasing the kinetic energy of the particles. So at that first stage, at the third stage, and the fifth stage, as I'm heating it, I'm increasing the kinetic energy of the particles. They're moving around faster and faster. So what's happening at this second stage here? The temperature has got to 50 degrees, and all of a sudden the temperature remains constant. That's not right, is it? I mean, surely when you heat something up, the temperature will just keep on increasing. Well, it doesn't. What's actually happening is the temperature stays constant because what you're doing to this substance is you're not making the particles move faster, you're breaking the bonds between the particles. What we're doing here is we're increasing the potential energy between the particles. We're breaking the bonds, overcoming the electrostatic forces between them, and allowing them to move around each other more. So this here, where you have the temperature being constant, doesn't mean that we're not giving the particles energy. It just means that we're not giving the particles kinetic energy. And what we've got here is a change of state. So where you have it, where you're transferring energy to or from a substance and the temperature is constant, you have a change of state. So there are two changes of state here. So we're going to work out which change of state it is. So first off, we're giving this substance heat energy. So the changes of state are going to be things like melting or boiling. But which is which? Well, if you look, we've got two changes of state here. So one's going to be melting, one's going to be boiling. Melting comes before boiling when you heat up a substance. So this first one here, 50 degrees, that is melting. Melting, remember, is where you go from solid, so this must be a solid here, to a liquid. And if you look, you can actually tell that the melting point is 50 degrees. If we go across there, it's 50 degrees, obviously use a ruler. So if we look at this other change of state here, we've got another change of state. This one, well, if in this light blue section it's a liquid, this section up here, it must be a gas. Let's move that out of the way. So this change of state is going from a liquid to a gas, so that there is boiling. And you can see here that the boiling point is 80 degrees Celsius. Now, sometimes when we actually make these graphs, you won't get a really, really nice graph like this. You'll get a graph that's probably a bit sort of like that. So the temperature here, when changing state, should be nice and constant. Sometimes it isn't. That's due to the purity of the substance. It's how we measure how pure a substance is by looking at the boiling point and seeing if we get a nice flat line there, seeing if the temperature is constant. So now we need to look at what happens if you cool a substance. So when you cool a substance, you'll get a very similar graph, but this time it just follows the opposite of that. So you can see change of state here, that's temp and that's time. And this change of state here, well, it's supposed to be a gas up here, a liquid here, a solid here. So this one here must be condensing or condensation, and this one here must be freezing. Just remember, when something freezes, it doesn't necessarily have to be extremely cold. It just needs to be at the freezing or melting point or lower. People just get confused with that because they think of water, therefore it has to be cold in order for it to freeze. So we need to look at this thing called specific latent heat, what it actually means. Specific latent heat is to do with an amount of energy. It's how much energy it requires to change the state of a kilogram of a substance. So if you think of like a block of ice, for example, if you want to change the state of that ice, you need to give it energy. Now, how much energy you give depends on two things. One, what it is, well, it's water or ice. Two, it also depends on how much you've got. If you have more ice, so greater mass, you're going to need more energy. It also depends as well on the change of state. So if you have water, for example, the amount of energy required to melt water is different to the amount of energy required to boil the water. So when we talk about specific latent heat, the amount of energy required to change the state of 1 kilogram of a substance, we have two different specific latent heats. We have the specific latent heat of fusion, which is to do with melting or freezing, and the specific latent heat of vaporization, which is to do with boiling or condensation. So if you like, the specific latent heat of fusion is the amount of energy required to melt a substance per kilogram, or you could say the amount of energy required to change a kilogram of a solid to a liquid. And then specific latent heat of vaporization is the amount of energy required per kilogram to change liquid into a gas. You could also say vice versa. Just remember, I've talked about heating here. We could talk about cooling. If you had a kilogram of, let's say, steam, that's a lot of steam. If you had a kilogram of steam, if that condensed, that will actually release energy. So if, for example, you are very stupid and put your hand over the kettle, the reason why your hand burns is because when the steam rises up, it will go to your hand and it will condense on your hand. It will change from a gas to a liquid and it will release energy. That energy is transferred to you, hence why it burns you. So when you're going from melting and boiling, you're transferring energy. But when a substance goes, when it's condensing or it's freezing, it gives the energy back out. So just remember that. So I just want to look at this compared to specific heat capacity because they both have something in common. Both of them are to do with energy. It's how much energy is required. Both of them are to do with a kilogram. So they're both amount of energy required per kilogram to do something. But the difference is what it's to do. Specific latent heat is to change the state. Specific heat capacity is to change the temperature by 1 degree Celsius. A little fact you just need to add in there, specific latent heat, you could also say where there is no temperature change. Okay, so when you are changing the state, there should be no temperature change. So let's look at calculating specific latent heat. Here is the equation. This equation you do not need to remember. It is given to you in the formula book. So latent heat is the amount of energy required to change the state of a kilogram of a substance. Remember, there is the specific latent heat of fusion, which could be solid to liquid or liquid to solid, and the specific heat of vaporization, which is liquid to gas or vice versa. Mass is always kilograms. It should be a lowercase k. That should be kilograms. It's the only thing that has the prefix kilo in front of it. Energy is measured in joules, if you're being lazy, capital J. And then specific latent heat is joules per kilogram, because remember, it's how much energy per kilogram you need to change the state of a substance. So here's a practice question. Read through it very carefully. Pause it and I will give you the answer. Okay, so if we look through this, same thing as always. We write down the equation and we leave the gaps. Mass, 2 kilograms. We don't need to change that. Mass is measured in kilograms. Specific latent heat. Now look very carefully. I've been really nasty here. 340 kilojoules per kilogram. So there's two ways of doing this. If you said that was 340, you could do 2 times 340 and it will give you 680. But your answer won't be in joules. Your answer there will be in kilojoules. Because what you're saying is that that's 340 kilojoules per kilogram. You've got 2 kilograms. So that'd be 680 kilojoules. An easy way to do it, if you want to understand it, 2 times 340,000 joules per kilogram, and therefore you'll get 680,000. That was a nasty little trick there. I just didn't want to give you a really easy question for you to have a go at. Oh, I've done the work in there. Right, here's some practice ones. Press pause if you want to have a go at them, and I will go through the answers. Okay, just a few things to note when you're going through these. Whenever you see prefixes that's not kilogram, change them straight away. So look, 190 megajoules. Mega is 1 times 10 to the 6, which means a million. So that would be 190 million joules. Standard form. You might want to write that out like that. If you're not sure on standard form, write out standard form in your calculator, press equals. As long as it's not too small or too large, you can actually see what the number is if you're not sure how to convert numbers from normal to standard form. Second one there, look, watch out for that, 500 grams. There are 1,000 grams in a kilogram, so you have to do 500 divided by 1,000, which will give you 0.5. And then here, look, I've been really sneaky again, that's 340,000 joules per kilogram. Just wanted to show you this challenge one here. Be very careful. Sometimes this will be useful, but actually it's not. Specific latent heat of the energy required to change the state of a substance per kilogram. The equation is energy is mass times specific latent heat. Well, there's your mass, 500 grams, 0.5 kilograms. There's your specific latent heat. This number here is actually pointless at the minute. Something to throw you off the scent, but it will be very handy in the future. Here are the answers. I believe there might be a mistake in there. There should be an extra 0 there. My apologies. Look out for this as well. Sig fig. They will ask you these in questions. It's good to get into a routine of knowing how many sig fig to quote it to. You quote it to the lowest number that you have in a question. So look, there's 2 there. But yeah, if it says 2 sig fig, if you've got no idea what to do in the question, time some numbers together, and if it says 2 sig fig, give your answer to 2 sig fig. You should gain a mark for at least doing that. Okay, now here's a tricky question. 2 kilogram block of ice is at 0 degrees Celsius. It's heated until it melts and is now at 20 degrees Celsius. How much energy is required to do this? Right, so what we're doing is we're doing 2 things. If we made a graph of this and we said there's time there and temperature there, what we're doing is we've got 2 kilograms of ice. It's at 0 degrees Celsius, so let's just say 0 is here. We're heating it until it melts, and now it's at 20 degrees. So what we're doing is we're doing this. We're heating it, it melts, and then we heat it some more, and it increases from 0 to 20. So first off, we're going to need energy to do that stage, and energy to do that stage. So energy to change the state, that's given by this equation. So E equals m times L. Let's substitute the numbers in. The energy required is the mass, well that's 2, times the specific latent heat, which is 340,000 joules. So 2 times that will give you 680,000 joules. Right, the second stage, we're changing the temperature here, so we need this equation. So we need E equals, or delta E, equals m times C times delta theta. Mass is 2. Specific latent heat of water is 4,200. The change in temperature is 0 to 20, so that's 20 degrees Celsius. So all we need to do is do 2 times 4,200 times 20, and that will give you 168,000 joules. Now what we need to do is we need to add that to 680,000 joules, and you should get 848,000 joules. That is the total energy required to do that. That is your answer. And just remember, 848,000, we could write that in standard form. We could write that as 8.48 times 10 to the 5. We could also write that as 848 kilojoules. So, skip that. Here are some more practice questions if you'd like to have a go at them. I will show the answers in a second if you want to pause. Okay, here we go. There we are. I've used a prefix there for that final answer. Right, now I want to show you this. This was a past paper question I saw and it was horrible. 5 marks. People hate these types of questions, but actually just break them down. They're really nice and easy and you can gain a few marks just doing very simple things. So ice cube is at minus 15 degrees. If anything, it might be easier doing that graph thing again. So we do time, we do temp. Right, so we're at minus 15 to start off with. So at minus 15, the total thermal energy needed to raise the temperature of this ice to 0 degrees Celsius and completely melted is 5848. So we are going from 15 to 0, minus 15 to 0, and then we're melting it. So we've got to do this again. We've got to work out how much energy to do at either of those stages. And if it tells you 5848 joules is how much energy is required to raise it from minus 15 to 0 and then melt it. The specific capacity is 2,100 joules per kilogram degree Celsius, and the specific latent heat of fusion of ice is 334,000 joules per kilogram. Calculate the mass of the ice cube. Right. So we need to just simplify this at the start. We're looking at stage, let's call this stage 1, stage 2. So at stage 1, we're increasing the temperature from minus 15 to 0. So that's to do with specific heat capacity because we're changing temperature. So specific heat capacity is equal to M times C times change in theta. Change in energy is equal to mass times specific capacity times change in temperature. Let's fill in the gaps. So the mass of this, we don't know what it is. So let's just call it M. The specific heat capacity of ice is 2,000, just going to move that, 2,100. And the change in temperature was from minus 15 to 0. So that is 15 degrees Celsius. So the amount of energy required to do that is M times 2,100 times 15. Let's just simplify that. I could simplify it by doing 2,100 times 15. The change in energy is equal to mass times 315,000. Oh, sorry, 350,000. 31,500. Now I can't simplify it further. So let's go on to the next stage. Stage 2, changing the state. So changing the state is given by this equation, E equals M times L. We don't know what the mass is, so let's just call that M. L is the specific latent heat of fusion, 334,000. And that is that. Just remember here, we're assuming that no water has evaporated in this case, because in real life, you won't have, if I change the state of ice that's minus 15 to 0, you may get some evaporation. You may even get some condensation of the water vapor in the air. We're assuming that there is no mass loss in this case. So what we've said is, in order to raise the temperature of this ice and then change the state of it, we needed energy to do that. And it said in this question, that's how much energy it needed. So what we could say is that this energy we needed, 5848, is equal to the energy in the first part plus the energy in the second part. So 5848 is equal to that plus that. So it's equal to, I'll do this in brackets, M times 31,500 plus M times 334,000. So if we simplify this, 31,500 plus 334,000 M, you should get 5848 is equal to 365,500 times M. Now, a nice bit of algebra here. We just need to do some simplification. So we need to do 5848 divided by, I'm just going to get rid of that. Oh, divide both sides by 365,500. Now that will simplify this right hand side to this, to m, the mass, and then do that 5848 divided by your answer, and you get 0.016 kilograms, which is mass. And look, because I'm an idiot, I've already revealed the answer down here. Now that might seem like quite a small number, 0.016 kilograms, but that's just 16 grams. That's not that much of ice. So that's that. Hope you've enjoyed, guys, and I'll see you next time.